Welcome back to the deep dive. Today, we're really getting into something crucial for making generative AI, well, actually useful in the real world. We're talking about how to tackle that fundamental, really frustrating problem that, every large language model faces right now. It kind of boils down to a date, 2021.
Yes, the
Yeah.
great knowledge cutoff. It's the big wall everyone hits.
Exactly. You could have this incredibly powerful LLM, right?
Yeah.
Does amazing things, writes poetry, writes code. But then you ask it something specific and recent, like tell me about the partnership announcement from November 14th, 2024.
Nothing.
Or worse.
It makes something up.
Right, because its knowledge just stopped somewhere back in 2021 or whenever it was trained. It hits this wall of ignorance. And if you're running a business, well, that's just not going to fly.
No, it's completely unacceptable. It highlights that core limitation. They're amazing generalists trained on, vast amounts of web text.
Yeah.
But they fail spectacularly as specialists on your recent data or, current events.
So that's our mission today, and it's really two parts. First up, we're going to properly unpack the main technical strategy that gets around this limitation. That's Retrieval-Augmented Generation, or RAG.
The workhorse for current data.
Yeah, exactly. And we're going to use some specific examples from our source materials involving LangChain and IBM tech to really map out how it works step by step, from getting a document in to getting that precise answer out.
But then, and this is crucial, once you get RAG working well, you sort of immediately bump into the next big challenge.
It is.
Complexity. Suddenly your simple AI app isn't so simple. You've got retrieval, maybe you need agents talking to other systems, you need guardrails for safety, ways to evaluate if it's even working. It gets messy fast.
Fragmentation. Chaos, as the sources call it.
Precisely.
Yeah.
So the second half of our deep dive today is looking at a framework designed specifically to tame that chaos. It's called Llama Stack. And the idea really is to bring some standardization, some order, almost like Kubernetes did for containers, but for these complex Gen AI application stacks.
Okay, so RAG to fix the knowledge gap, Llama Stack to fix the complexity it creates. We're drawing on some detailed technical guides for both of these today. This is really about moving Gen AI from being like a cool demo to something you can reliably build on in an enterprise.
Scaling it up responsibly.
Okay, let's unpack this.
Yeah.
All right, Section 1, the core strategy. Let's start with that baseline problem again, just to be crystal clear. The old way, the simple way is just user asks a question.
Query goes in.
Right. Query right arrow, LLM right arrow answer comes out, straight line, super simple interaction.
But as we said, the big if is if the answer needs knowledge, the model just doesn't have in its static training data.
And it's not just that it says, I don't know. Often it doesn't. It hallucinates, right?
Yeah.
It gives you a confident-sounding answer that's completely made up.
That's the really dangerous part. The model's designed to be helpful, to generate coherent text. So if it lacks the actual fact, its instinct, based on all the patterns it learned, is often to, well, invent something plausible sounding. It connects statistical dots that shouldn't be connected.
Leading to, potentially huge factual errors.
And the core issue here is that the LLM is fantastic at generation, but it has zero built-in capability for real-time information retrieval. It can't just go look something up.
So the challenge is, how do we give it that up-to-date, verified external information before it starts generating? How do we ground its answer in actual current truth?
And that is precisely what Retrieval-Augmented Generation RAG is designed to do. It's essentially like giving the LLM an open book exam, but the book is a curated library you provide.
Okay, so it integrates retrieval right into the generation process itself.
Exactly. It directly tackles that static knowledge limitation by feeding the LLM current external information relevant to the specific question being asked. It's no longer just relying on its old memories.
So if we break down that RAG workflow, it's obviously more complex than the simple query LLM answer chain. Can you walk us through the steps? How does the info get found and then given to the model?
Sure. It starts with building the knowledge base. Think of this as your curated, specialized library. It's a database, but instead of typical data, it's filled with the content you want the LLM to know about.
So this could be anything. Internal documents, product manuals, recent news articles.
Absolutely. Company reports, legal texts, support documentation, or like in the examples we looked at, specific recent articles scraped from a website like IBM.com. The key is the quality and relevance of this data directly determines the quality of the final answer.
Okay, got the knowledge base. Now, the user asks the question, maybe what were the main points of the November 14th partnership? How does the system find the right document or maybe just the right paragraph from potentially thousands or millions of documents in that base?
That's the retriever's job.
Mm.
It's the smart librarian. When the user's query comes in, the system doesn't just do a keyword search across everything. No, it first converts the user's question into a mathematical representation, a vector.
Embedding.
Exactly. And the retrievers then searches the vector store where all the document chunks have also been turned into vectors, looking for the chunks whose vectors are mathematically closest, meaning semantically most similar, to the question vector.
So it's finding related concepts, not just matching words.
Precisely. It pulls back maybe the top, say, 3 or 5 most relevant chunks of text from the knowledge base. These top results are then gathered together.
And this becomes the prompt context. But it's not just the raw text chunks dumped into the prompt, is it?
No, that's a critical point. The prompt context is carefully constructed. It includes the retrieved text chunks, yes, but also, crucially, very specific instructions for the LLM.
Like what kind of instructions?
Things like, you are an AI assistant. Answer the user's question based only on the following provided context. Do not use any prior knowledge. If the answer is not found in the context, state clearly that you do not have enough information to answer. You have to be explicit.
Okay, so you're walling it off from its general knowledge and forcing it to use only the provided snippets.
You are. So now you have this bundle, the original user query, the retrieved relevant context snippets, and these strict instructions. This whole package goes into the next step, LLM augmentation.
This is where the LLM finally sees the question.
Right, but it sees it in this completely new, augmented way. The LLM's task fundamentally changes. It's not being asked to recall general information anymore. It's being asked to perform a reading comprehension and synthesis task based only on the current contextual data you just handed it.
And then finally, generation.
Yep. The LLM generates the answer. But now, because it was constrained to use only the provided context, the answer should be precise, factually grounded, and verifiable. You can trace it back to the specific documents you loaded into your knowledge base.
The static knowledge cutoff problem is effectively bypassed.
It is. For that specific query using that specific knowledge base.
And the sources we looked at really showed this works in practice, didn't they? They tested it against that exact November 14th, 2024 UFC-IBM partnership query we mentioned.
They did. Before AG, the base model knew nothing. After loading that specific article into the knowledge base and running the RAG-I process, boom, the system could answer accurately.
And it wasn't just news. It worked for technical stuff too, right? Like defining specific product terms.
Yeah, they tested it asking things like, what is watsonx.data? Or explain watsonx.ai. Again, the base model might waffle or hallucinate. But with the relevant IBM product pages loaded into the RAG-I knowledge base, the system pulled out the correct, precise definitions directly from that source material.
So it proves RGAN turned that generalist model into a reliable specialist, at least for the domain covered by your knowledge base.
Exactly. A verifiable domain expert based on the data you give it.
Okay, so we know ARG works conceptually, and it solves a massive problem. Now we need to get into the weeds a bit, the technical how-to, section 2. Deep dive into RGAM implementation. How do you actually build that knowledge base and make it searchable? This is where those LangChain implementation details from the source material are super helpful.
Right. And before we even jump into the steps, we have to talk setup. Prerequisites. Especially if you're using serious enterprise-grade models like the IBM ones mentioned.
It's not just pip install something, is it?
No, not quite. You'll definitely need credentials, things like an API key, maybe a project ID for the platform you're using, like watsonx. You need to install a bunch of Python libraries, LangChain itself, maybe specific loaders, the vector database client, the LLM client library.
And security is key here.
Absolutely paramount. You can't just hard code your API key in the script. Best practice, as highlighted, is using environment variables, typically loaded securely from a .env file that's not checked into your code repository. Basic security hygiene, but critical in enterprise.
Okay, environment setup, credentials secure. What's step 1 in the actual RShay build?
Step 1 is the big one, building of the vector store. This is all about gathering that external knowledge and getting it ready. It starts simply off by defining your sources.
Like that list of 25 URLs in the example.
Exactly. You specify where the knowledge lives. Then comes loading and cleaning. You use a tool, like LangChain's web-based loader in the example, to actually fetch the raw content from those URLs.
But web pages are messy. HTML tags, ads, navigation menus.
Incredibly messy. You can't just vectorize raw HTML soup. You must clean it. The sources mention removing excessive whitespace, line breaks, maybe stripping out common boilerplate text. This cleaning step is often underestimated, but it's vital. Garbage text in means garbage vectors, which means garbage search results later.
Right. Okay, clean documents loaded. Now here's where it gets really interesting. We hit the critical process of chunking. Why can't we just vectorize a whole clean document? Why break it up? And what's this recursive splitting about?
Yeah, this is super important and often a point of confusion. The main reason is a hard constraint, the LLM's context window.
The amount of text it can actually process at once.
Exactly. Even the biggest models have a limit on the number of tokens, words, or parts of words they can handle in a single prompt. If you retrieve a massive 50-page document and try to stuff it all into the prompt along with the question,
It'll break. Or just ignore most of it.
it'll likely fail with an error, or, the model might effectively forget the beginning of the context by the time it reads the end. It just exceeds the operational limits.
Yeah.
So you have to break the large documents into smaller, digestible chunks.
And the source mentioned using a specific technique, recursive character text splitter. Why recursive?
The recursive part is clever. Instead of just blindly chopping the text every, say, 500 characters, it tries to be smarter. It uses a predefined list of separators, often starting with double new lines, paragraphs, then single new line sentences, then spaces, and finally any character.
So it tries to keep paragraphs together first, then sentences.
Exactly. It recursively tries to split along the most natural semantic boundaries first, aiming to keep related ideas within the same chunk as much as possible. It's generally better than just a fixed-size chop.
And the size of these chunks is also a tuning parameter, right? The example used 512 characters.
Yeah, chunk size is a key decision. Too small, and a chunk might lack sufficient context. Like you get a single sentence fragment that doesn't make sense alone. Too large, and you risk exceeding context windows or retrieving chunks that contain a lot of irrelevant information alongside the useful bit, which wastes tokens and can confuse the LLM. 512 characters is a common starting point, but you often need to experiment.
And they also mentioned chunk overlap. Why overlap the chunks?
Another subtle but important detail. Imagine a really important sentence starts at the very end of chunk A and finishes at the very beginning of chunk B. If you retrieve only chunk A, you miss the end of the idea. If you retrieve only chunk B, you miss the start.
So the overlap ensures the full sentence or idea might be captured even if the split happens right in the middle of it.
Precisely. A small overlap, maybe 50 characters like in the example, acts as a buffer. It increases the chance that if a relevant piece of text spans a chunk boundary, retrieving either chunk will still give the LLM the complete thought. It's a trade-off, adds a little redundancy, but usually improves retrieval quality significantly.
Okay, makes sense. So now we have these nice, clean, optimally sized, overlapping chunks of text. What's next?
Now we turn them into math. This is embeddings in storage. We need an embedding model.
Like the IBM Slate model mentioned in the source.
Right, you instantiate that model. Its whole job is to take a piece of text, one of our chunks, and convert it into a long list of numbers, a high-dimensional vector.
And the magic is that similar meanings get similar vectors.
That's the core idea. Semantic similarity translates to proximity in this high-dimensional vector space. Chunks talking about Q4 financial results will have vectors that are mathematically close to each other, even if they use slightly different wording. This is far more powerful than just keyword matching.
Okay, so every chunk becomes a vector. Where do these vectors live?
They get loaded into a specialized database called a vector store. The example uses Chroma, which is a popular open source option that can run locally. There are many others like Weaviate, Pinecone, Milvus. These databases are optimized for one thing: incredibly fast similarity searches on these dense vectors.
So your knowledge base is now effectively indexed by meaning.
Exactly.
Ready to be queried.
That covers step 1, building the store. Now, steps 2 and 3 are about configuring the engine that actually uses this store, right? Step 2 is setting up the retriever.
Yep. This is usually pretty straightforward once the vector store is built. You essentially take your Chroma instance, or whatever you used, and tell LangChain to treat it as a retriever, using a function like AssesRetriever.
And this is where you might specify how many chunks to retrieve.
Correct. You can often pass parameters here, like search corgus 3. That tells the retriever, when you do a search, just give me back the top 3 most relevant chunks. Choosing the right value for K is another one of those tuning exercises, balancing context richness with prompt length limits and potential noise. Got it. And step 3 is setting up the other key component, the generative LLM itself.
Right. You need to choose which LLM will actually write the final answer. The example uses an IBM Granite model. You instantiate a client for that model, providing your API key and project ID.
And you also set parameters for how it generates text.
Yes, crucial parameters. Things like max new tokens to control the maximum length of the generated answer, preventing runaway responses, and importantly, temperature.
Temperature controls creativity, right?
Essentially, yes. A temperature of 0 makes the model very deterministic, very focused, sticking closely to the most probable words. For RAG, where you want factual answers based only on the context, you typically want a low temperature, maybe 0 or zero point 0.1. A high temperature encourages more creativity, more randomness, which is usually the opposite of what you want in a factual Q&A system.
Okay, vector store built, retriever configured, LLM selected and tuned. Now, step 4, bringing it all together in the RAG chain. This creates the actual end-to-end process. We talked about the prompt template earlier. Why is getting this template right so critical?
It's arguably the most important non-vector part of the whole system. It's the control structure. It dictates exactly how the information is presented to the LLM. It needs placeholders for the retrieved context and the user's question.
And those explicit instructions we discussed.
Yes, embedded right in the template. Use only the provided context. Do not use prior knowledge. State if the answer isn't present. These instructions are the guardrails preventing the LLM from ignoring your carefully retrieved context and just falling back on its general, potentially outdated or irrelevant, internal knowledge. Crafting a robust prompt template is an art and science in itself.
And the sources also mentioned a little helper function sometime.
Yeah. Often you need a small function just to format the retrieved documents before they go into the template's context placeholder. The retriever might just give you back a list of document objects. This helper function would extract the actual text content from each, maybe number them, put clear separators between them, just to make it really clean and unambiguous for the LLM.
So the final arg chain links all these pieces.
Exactly. You use something like LangChain expression language, LCEL, to define the sequence. First, the user question goes to the retriever to get context. Second, that context and the original question goes through the helper function for formatting. Third, the formatted context in question are plugged into the prompt template. Fourth, the completed prompt goes to the LLM for generation. And finally, the LLM's output is parsed.
It connects the retriever, the formatting, the template, and the LLM into one single executable chain.
That's it. One call to this chain triggers the whole RAG process, turning a question into a context-aware, grounded answer. It's an elegant way to orchestrate the whole flow. Okay, so that R game may be running nicely on a developer's machine using LangChain, pulling from a local Chroma DB that feels like a huge win. And it is.
I sense a but coming.
There's always a but when you scale things up.
Yeah.
That elegant RAG implementation, while solving the knowledge problem, immediately throws us headfirst into the next big challenge. The complexity of real-world enterprise deployment. The challenge of scale.
Right. You hinted at this earlier. Solving the data problem creates an infrastructure problem.
It absolutely does. That single RA chain is a proof of concept, maybe a departmental tool. But think about building serious production-grade AI applications for a large organization. The requirements just explode way beyond a simple LLM call and retrieve.
So what are these extra components that start piling up and make the stack, as the sources put it, chaotic?
Well, first, even within a RAG, you get advanced data retrieval. You're probably not hitting just one little Chroma DB. You might need to query multiple vector databases, maybe Weaviate for product info, Pinecone for support tickets, a different one for HR docs, potentially across different security zones, maybe needing different embedding models. Just the retrieval part gets complicated.
Okay, so diverse data sources. What else?
Then you inevitably move towards agent functionality. You don't just want the AI to answer questions, you want it to do things.
Like book a meeting, update a sales record, run a database query.
Exactly. Interacting with external APIs and systems. Suddenly your AI needs tools, and managing those tools, their permissions, their execution, that's a whole new layer of complexity. Think multi-step reasoning, planning.
And then there are the operational necessities, right? The stuff platform teams care deeply about.
Oh yeah, you need robust evaluation frameworks. How do you even know if your complex RA agent system is working well? You need metrics, test sets, maybe human-in-the-loop validation. You need observability, detailed logging, tracing across all these distributed components, monitoring for performance bottlenecks or failures. Trying to debug why a 5-step agent call failed without good observability is a nightmare.
And the big one, security and compliance.
Non-negotiable. Guardrails. You absolutely need layers of protection. Preventing sensitive data leaks, ensuring the AI complies with regulations like GDPR or RIA-Pay, filtering out harmful or biased outputs, making sure the agent doesn't take disallowed actions. These aren't optional extras in an enterprise, they're fundamental requirements.
Okay, so you've got retrieval from diverse sources, agents using tools, evaluation, observability, guardrails. If every single team inside a company builds this entire stack themselves,
Using different tools for each layer.
maybe one team uses LangChain, another uses Llama Index, another rolls their own Python scripts, different vector DBs, different monitoring tools.
That's exactly how you get the chaotic, fragmented mess the sources describe. Each application becomes a unique, brittle snowflake. It's incredibly hard to manage, update, or secure consistently.
If the central platform team wants to, say, upgrade the security guardrail component or switch to a cheaper vector database provider,
They have to go into potentially dozens or hundreds of different bespoke application stacks and figure out how to rip out the old component and plumb in the new one without breaking everything. It's slow, it's risky, it stifles innovation.
this lack of a common standard, a common way of plugging these components together, is the core problem.
It is. You end up with this massive integration headache and operational burden for both the developers building the apps and the platform teams trying to support them. This is exactly the pain point that necessitates a standardization layer.
Which perfectly sets up the need for something like Llama Stack, a way to impose order on this generative AI chaos.
Precisely. A way to manage the complexity, provide portability, and give control back to the platform teams and developers.
Okay, section 4, Llama Stack. We've established the chaos that emerges when you scale Gen AI apps. How does Llama Stack propose to fix it? What's the core idea behind this standardization framework?
The core idea is actually pretty elegant, drawing inspiration from established patterns in cloud infrastructure. It's about architectural separation via a common central API.
Okay, break that down. What does a central API mean here?
It means Llama Stack itself doesn't try to be the LLM or the vector database or the guardrail system. Instead, it defines a standardized way to talk to those components. It provides a consistent application programming interface, an API, for the essential functions needed in a Gen AI workload.
So the application code talks to the Llama Stack API, not directly to, say, a Llama or ChromaDB.
Exactly. The application requests, for example, generate text via the Llama Stack inference API. Llama Stack then routes that request to whichever actual inference engine, the provider, has been configured underneath. This creates a layer of abstraction.
And this abstraction is what enables customization and swapping.
Precisely. Because the application only codes against the standard Llama Stack API, the platform team can easily swap the underlying provider, maybe change the LLM provider or the vector store provider to meet specific needs like cost, performance, privacy regulations, or data residency requirements without forcing the application developers to rewrite their code. It's modular. Plug and play.
And which parts of the stack does Llama Stack focus on standardizing? You mentioned key interfaces.
Right now, the focus is on standardizing the interfaces for the most critical and complex parts. Inference, the actual text generation, agents, managing tools and multi-step actions, and guardrails, handling the safety, security, and policy enforcement. By providing standard APIs for these, it covers a huge chunk of the complexity in modern AI apps.
This really clicks when you bring in the Kubernetes analogy. That's the key insight for listeners, I think.
It really is a powerful analogy. Think about what Kubernetes did for containers. Before K8s, you had Docker. You had other runtimes, different ways to manage networking, storage. It was fragmented.
Right.
Kubernetes came along and defined standard objects like the pod, the service, the ingress. It provided a standard API to declare what you wanted. Example, I need 3 replicas of this container image exposed on this port.
And you could then plug in different underlying technologies, right? Different container runtimes, Docker, container, different network plugins, different storage providers.
Exactly. Kubernetes standardized the control plane, the API, allowing interchangeability underneath. Llama Stack aims to do the exact same thing, but for the generative AI application layer. It defines the standard APIs for things like inference or agent tool use.
So your application interacts with the standard Llama Stack API.
And underneath, you can plug in different providers for inference, like Llama, VLLM, maybe cloud providers API, different providers for vector storage, different providers for guardrails, and so on. It applies that successful Kubernetes pattern to the Gen AI stack.
That makes the value proposition much clearer. Now, a point of potential confusion. The name Llama Stack. Does it only work with Llama models from Meta?
That's a great question, and the answer is emphatically no. The sources are very clear on this. Despite the name, Llama Stack is designed to be model independent.
So it can orchestrate calls to Mistral models or IBM's Granite models or Cohere models?
Any model, really, as long as that model can be served or executed by one of the supported underlying inference providers. Common providers like Llama or VLLM themselves support a wide range of open source models. So if a Llama can run a Mistral model, Llama Stack can orchestrate inference calls to that Mistral model via the Llama provider. The focus is on standardizing the call to the inference engine, not locking you into a specific model family.
Okay, that's crucial. It's about the infrastructure standard, not the model itself. Let's really cement this core concept.
Yeah.
The separation between the API and the provider. This seems to be the absolute heart of how Llama Stack achieves interchangeability.
It is the fundamental principle. You have to think of them as two distinct layers. One, the API, the interface. This is defined by Llama Stack. It specifies what capability is being requested abstractly. For example, the inference API defines what parameters are needed to ask for text generation, prompt, temperature, max tokens, etc. The vector I/O API defines what is needed to store or retrieve vectors. Two, the provider, the implementation. This is the specific piece of software or service that actually does the work. It dictates how the API request is fulfilled. It's the concrete engine running underneath the abstract API.
So give us some concrete examples. For the inference API, what providers could be swapped in?
Okay, perfect example. A developer writes their application code to use the Llama Stack Inference API. Scenario 1, local dev. They configure a Llama as the provider. A Llama runs models locally on their laptop. Great for quick iteration, offline work. Scenario 2, production scale. For deployment, they change one configuration setting to point the Inference API provider to VLLM. VLLM is a high-throughput engine optimized for serving LLMs on powerful GPUs in production. Much faster. Handles concurrent requests. Scenario 3, hosted speed. Maybe they need extreme low latency. They could change the config again to use Grok as the provider, which offers very fast inference via their hosted API. The key is, the application developer's code, the part that calls the Llama Stack Inference API, did not change at all between these three scenarios.
Yeah, and the same principle applies to other parts, like vector storage.
Exactly. The application uses the Llama Stack Vector I/O API. Underneath, you could configure ChromaDB as the provider for local development. Then, for production, you might swap the provider configuration to use a managed Weaviate cluster, or maybe another cloud-based vector store. Again, the application code interfacing with the Vector I/O API remains untouched.
So the ultimate benefit is this complete decoupling. Application logic is separate from the underlying infrastructure implementation. That really is the definition of portability and avoiding vendor lock-in.
It is. It gives platform engineers immense control over the underlying stack for cost optimization, performance tuning, security compliance, while freeing up developers to focus purely on building the features and logic of the AI application itself, using stable, standardized interfaces.
Okay, let's ground this standardization theory in Section 5. Practical applications and portability. How does Llama Stack actually make life easier in common scenarios? Let's start with the absolute most frequent enterprise use case, chatting with your own documents.
Right. This is where Llama Stack's portability promise really shines, especially across the typical development lifecycle. Think about a team building a RAG app to query internal technical documentation.
Where do they start?
They almost always start locally. Speed of iteration is everything initially. So they'd likely use what Llama Stack calls a local hosted distro. This typically bundles a Llama for running a decent-sized LLM locally for inference, and maybe ChromaDB for the vector store, running right there in containers on their laptop or dev server.
Okay, quick setup, easy to test and debug.
Exactly. But then, inevitably, they hit the limits of local hardware. The application proves valuable, and they need to scale it up for wider use, maybe handle hundreds of concurrent users.
And this is where the pain usually starts, right? Rewriting deployment scripts, changing API endpoints, dealing with new authentication.
That's the fragmentation nightmare Llama Stack aims to eliminate. Because they built their RAG application against the standard Llama Stack Inference API and Vector I/O API, moving to production becomes primarily a configuration change.
How so?
They simply update the Llama Stack configuration for their deployment environment. They swap the inference provider from a Llama to, say, VLLM, running on beefy GPUs in the cloud or data center. They swap the Vector I/O provider from the local ChromaDB instance to a managed, scalable enterprise vector store provider.
And the core chain logic in their application.
It is exactly the same. The code calling llamastack.inference.generate or llamastack.victorio.search doesn't need to change. This ability to seamlessly lift and shift the application from a local dev setup to a high-performance production environment is a massive win for operational efficiency and reliability.
Now, you mentioned distros distributions. How do they simplify this setup process? Are they like pre-packaged bundles?
That's a good way to think of it. Distros are predefined collections of Llama Stack providers, essentially recipes or templates, curated and validated for specific environments or use cases.
So instead of configuring a Llama and ChromaDB individually, you just pick the local development distro.
Pretty much. It simplifies setup and helps platform teams enforce standards you might have. Local hosted distros. Bundling providers like Llama and ChromaDB optimize for running self-contained on laptops, edge devices, maybe even air-gapped environments. Remote distros. These configure providers that point to external, potentially third-party managed services or APIs. For example, a remote distro might configure the inference provider to use a specific cloud vendor's LLM API endpoint and the vector I/O provider to use their managed vector database service. The developer might only need to provide an API key.
So distros make it easier to get started and ensure consistency across different deployment targets.
Yes, these streamline the bootstrapping and configuration process significantly.
Okay, RAG portability makes sense. But Llama Stack isn't just for RAG. You mentioned it handles advanced functionality like agents that need to interact with tools. How does it manage that without hard-coding tool logic into the agent? You mentioned something called MCP.
Right, Model Context Protocol, MCP. This is the key abstraction layer Llama Stack introduces for agent tool use. Think about what an agent needs to do. Maybe update a Salesforce record, send a Slack message, query a Postgres database.
Actions in the real world.
Exactly. The traditional, brittle way is for the developer building the agent to write Python code that directly makes the Salesforce API call or directly connects to the database and runs SQL.
Which means the agent code is tightly coupled to the specific implementation details of those tools.
And that's fragile. If the Salesforce API changes or the database schema is updated or the security requirements for accessing Slack change, you have to go find and modify the agent's core logic. It doesn't scale, and it's a security headache.
So how does MCP decouple this?
MCP introduces the idea of MCP servers. An MCP server is a separate, standalone service whose job is to register a related set of functions or tools and expose them via a standardized protocol. You might create an MCP server specifically for interacting with your company's CRM. You would register functions like create lead, update contact, get account details.
So the MCP server holds the actual implementation logic for talking to Salesforce.
Exactly. It encapsulates that specific tool knowledge. Then, the CRM tool group, provided by the MCT server, is registered within the Llama Stack infrastructure, just like an inference provider or a vector store provider is registered.
Ah, okay. So the agent doesn't talk directly to Salesforce. It talks to Llama Stack, requesting a tool from the registered CRM tool group.
Precisely. The agent's code becomes much simpler and more abstract. It might just say, I need to use the create lead tool from the CRM group with these parameters. Llama Stack routes this request to the appropriate pre-registered MCP server, which then executes the actual Salesforce API calls securely.
This sounds very much like how microservices use service discovery in APIs.
It's a very similar architectural pattern. The agent code is completely decoupled from the tool's implementation details. Developers can focus on the high-level logic of the agent, whether it's a simple sequence of steps, prompt chaining, or a more complex autonomous agent using reasoning, React agents, knowing that the actual execution of tools is handled securely and consistently via registered MCP servers.
So for those complex React reasoning and acting agents, where the model thinks, decides on an action, a tool call, gets the result, thinks again, Llama Stack standardizes that whole acting part.
It does. It ensures that when the agent decides, okay, my thought process says I need to query the database, the subsequent call to the database tool group via Llama Stack is secure, monitored, and conforms to enterprise policies, regardless of whether that tool ultimately talks to Postgres, MySQL, or something else defined in its MCP server. It separates the agent's reasoning context from the tool's execution context.
Okay, putting it all together, what's the overarching goal here for an organization adopting something like Llama Stack?
The ultimate goal is to empower both platform engineers and application developers. It gives platform teams the levers they need to govern, manage, and optimize the entire generative AI platform infrastructure, choosing providers, enforcing security, ensuring observability without having to build every single integration point from scratch.
And for developers?
It frees them from the underlying infrastructure complexity. They can focus on innovation, on building sophisticated, scalable, and truly portable AI applications using standardized interfaces for inference, retrieval, agents, and guardrails. They don't need to become experts in 3 different vector databases or 4 different LLM serving frameworks.
So it shifts the focus back up the stack towards the application's value.
It's exactly. Abstracting away the necessary but complex infrastructure plumbing allows teams to move faster and build more robust, maintainable AI solutions. The sources mention the initial steps often involve local deployment using containers, like Docker or Podman, making it accessible to get started, but the real power unfolds at the enterprise scale. So just to synthesize what we've really dug into today, we've seen two critical frameworks. First, Retrieval-Augmented Generation, RAG. It's the core technique, the essential workaround, for that fundamental LLM knowledge cutoff problem.
Right, it makes models current and relevant by feeding them external data through that whole workflow.
Right.
Loading, cleaning, chunking, embedding, retrieving, and then generating based on context.
Exactly. It modernizes LLM knowledge. But then building real applications with RAGs, especially adding agents and guardrails, creates significant infrastructure complexity.
Hmm.
And that's where the second framework comes in, Llama Stack.
The standardization layer, acting as that operational control plane, almost like a Kubernetes for Gen AI. It uses that API versus provider separation
Yep, that interchangeability principle.
to make these complex, multi-component AI application stacks manageable, scalable, and crucially, portable across different underlying technologies in an enterprise setting.
So hopefully, if you've been listening, you now have a much clearer picture, not just of how to technically solve the LLM knowledge cap using the RAG workflow details we discussed,
But also how the platforms themselves are evolving to manage the complexity that RAG and agents create, how Llama Stack's standardization approach aims to tame that chaos and give you back control. So what does this all mean? Where does this leave us?
Well, I think the big picture painted by the sources is that we're seeing a clear shift. AI is moving away from these monolithic, static black box models.
Toward more dynamic, interconnected systems.
Yeah.
Systems that can retrieve real-time data, interact with other tools, and operate within defined safety boundaries.
Precisely. RAG is the first step in that direction, and standardization layers like Llama Stack are the necessary infrastructure to make those interconnected systems practical and manageable at scale.
Which brings us to a final provocative thought, maybe something for you to chew on. If Llama Stack, or frameworks like it, truly deliver on this promise, if swapping out your core inference engine going from, say, a local Llama setup to a high-speed production VLLM instance, or even trying out a completely different provider like Grok really becomes as simple as changing a configuration file. What does that really mean for the classic problem of vendor lock-in in the AI space? And what does it mean for the sheer speed at which companies can adopt newer, better, maybe cheaper AI models and infrastructure over the next, say, 2 years?
It fundamentally changes the game. It pushes towards true model agnosticism at the platform level, the ability to rapidly experiment with and deploy the best fit model or infrastructure component for the job without massive re-engineering effort could become a significant competitive advantage.
It lowers the barrier to innovation and keeps vendors honest, maybe.
Potentially, yes. It encourages focusing on the value delivered by the models and tools, knowing the underlying plumbing can be swapped more easily. That acceleration in platform adaptability.
Yeah.
That's definitely something to watch.
A really powerful idea to end on. The infrastructure might finally be catching up to let the AI innovation truly fly. Thanks for breaking all that down.
My pleasure. It's a fascinating space right now. Looking forward to the next one.
Absolutely. We'll catch you next time on The Deep Dive.